Still on work, energy, and power. Let's use what we've learned so far about potential and kinetic energy to solve a few problems. Let's say we wanted to find the velocity of the block when it was 5 meters away from the wall, assuming the block started from its initial position at rest. We're also going to neglect friction in this case, and we take the mass of the block to be 17 kilograms. From the work energy principle, we know that the work done on the block is equal to the change in its kinetic energy. So we can write that W equals half mv2 squared minus half mv1 squared. We obtained the work done on the crate to be 468.75 joules. We know that its mass is 17 kilograms and that its initial velocity is equal to 0 meters per second because it starts from rest. So plugging all these values into our equation, we can calculate the final velocity or the velocity at the point where it is 5 meters away from the wall. And so we have 468.75 equals half of 17 times v2 squared minus half of 17 times 0 squared, which gives us 0, of course. So we have 468.75 equals 8.5 v2 squared. Solving for v2, we eventually arrive at 7.43 meters per second as our final velocity of the crate. For another problem we might want to solve, let's assume an object was dropped from a height of 11 meters above the Earth's surface, and we want to find the change in its velocity when it falls to a height of 3 meters above the Earth's surface. We're going to take the mass of the object to be 2 kilograms and the acceleration due to gravity as 9.8 meters per second. At 11 meters, we can use the relation U equals mgh to calculate its potential energy at that point, and we're going to call it U1. So U1 equals 2 times 9.8 times 11, which gives us 215.6 joules. And at 3 meters, we're going to call its potential energy U2, and U2 equals 2 times 9.8 times 3, which gives us 58.8 joules. So its change in potential energy is going to be equal to its final potential energy minus its initial potential energy, which is equal to 58.8 minus 215.6 joules, which gives us minus 156.8 joules. We see that its change in potential energy is negative, meaning that in dropping from a height of 11 meters to a height of 3 meters, its potential energy has reduced. Now we want to find its velocity when the object is at a height of 3 meters above the Earth's surface. From our work-energy relation, we know that the work done by gravity on the object is equal to the change in its kinetic energy. So we can say that the work done is equal to half mv2 squared minus half mv1 squared, where v2 refers to its velocity at a height of 3 meters and v1 refers to its velocity at a height of 11 meters. We also know that the work done by gravity on the object is equal to its initial potential energy minus its final potential energy, which is the negative of the change in the object's potential energy. So we know that the work done by gravity on the object is equal to 156.8 joules. Therefore, 156.8 joules, which is the work done, is equal to half of 2 times v2 squared minus half of 2 times 0 squared. And so v2 squared equals 156.8. And we obtain v2 as 12.52 meters per second. Apart from kinetic and potential energy, which are forms of mechanical energy, we have many other forms of energy. Some of them include electric energy, nuclear energy, thermal energy, and chemical energy. Energy can be transformed from one form to another and can also be transferred from one object to another. Whenever energy is transferred or transformed, it is found that no energy is gained or lost in the process. This is the law of conservation of energy, and it can be properly stated as: the total energy is neither increased nor decreased in any process, but energy can be transformed from one form to another. and transferred from one body or object to another. Let's assume we have an object which moves under the action of a conservative force F from position x1 to x2. From our work energy principle, we know that the work done by the conservative force equals the change in the object's kinetic energy. So we can write that work done is equal to the final kinetic energy minus the initial kinetic energy, which is equal to half mv2 squared minus half mv1 squared. Also, from our definition of potential energy, the work done on an object by a conservative force is equal to the initial potential energy of the object minus the final potential energy of the object. And so our work done is equal to U1 minus U2. Therefore, we can write that U1 minus U2 equals half mv2 squared minus half mv1 squared. And rearranging this, we have U1 plus half mv1 squared equals U2 plus half mv2 squared. This is the law of conservation of mechanical energy, which states that in a conservative system, the sum of potential and kinetic energies at one point is equal to the sum of potential and kinetic energies at another point. To demonstrate how we can use the conservation of mechanical energy to solve problems, let's suppose we have another object falling, but this time with an initial velocity. So we know that the object has a velocity of 5 meters per second when it is 18 meters above the ground level of the Earth's surface. And we also know that since it is under the influence of the Earth's gravitational pull, it will continue accelerating and therefore its velocity will continue increasing. So we want to know at what height above the Earth's surface would its velocity have doubled. To find the answer to this, we can use our equation for the conservation of mechanical energy. So we can write U1 plus half mv1 squared equals U2 plus half mv2 squared, where U1 is its potential energy at the initial height, V1 is its initial velocity of 5 meters per second, U2 is the height at which its velocity would have doubled, and V2 is its velocity when it's doubled, or 10 meters per second. We can further expand the potential energies and write mgh1 plus half mv1 squared equals mgh2 plus half mv2 squared. Now, since the mass of the object remains constant throughout, we can factorize its mass from both sides and cancel them out. So we're left with gh1 plus v1 squared divided by 2 equals gh2 plus v2 squared divided by 2. Plugging in our values into this equation, we get 9.8 times 18 plus 5 squared divided by 2 equals 9.8 times h2 plus 10 squared divided by 2, which further leads us to 188.9 equals 9.82 plus 50. Solving this equation for h2, we eventually arrive at h2 being equal to 14.2 meters. Power is defined as the rate at which work is done. Mathematically, we can write our average power as the work done divided by the time over which the work was done, or the time elapsed. Instantaneous power is defined as the average power over an infinitesimally small amount of time. So we can write that as the limit of the average power as delta t approaches 0. In SI units, power is measured in joule per second, which is given the name watt. We can define the efficiency of a machine as the ratio of its output power to its input power. To express this as a percentage, we simply multiply by 100. We can also define the efficiency of a machine in terms of work done. And so we can say the efficiency of a machine is defined as the ratio of work output to work input. And again, to express this as a percentage, we simply multiply by 100. Say we had a vehicle having a mass of 670 kilograms accelerating uniformly from rest to a velocity of 21 meters per second in 8.5 seconds. And we wanted to calculate the average power delivered by the engine of the car to give the vehicle such an acceleration. We could use the expression average power equals the work done divided by the time elapsed. Now, from our work energy principle, we know that the work done by the vehicle's engine is equal to the change in kinetic energy of the vehicle. So the work done is equal to half mv2 squared minus half mv1 squared, where v2 is the final velocity of the car, which is equal to 21 meters per second, and v1 is the initial velocity of the car, which is equal to 0 meters per second since the car started from rest. So we can write that the work done by the engine of the car is equal to half of 670 multiplied by 21 squared minus half of 670 multiplied by 0 squared. And this gives us 147,735 joules, or 147.7 kilojoules. Now the duration for which the vehicle's engine did this amount of work is equal to 8.5 seconds. So the average power delivered by the car's engine is equal to 147,735 divided by 8.5, and that gives us 17,380.6 watts, or 17.4 kilowatts.